Thank you. Check. OK, great. So hi, everyone. My name is Ruyi, and welcome to the session of theories and guidance. So I know it can be a little bit weird, but I would like to emphasize this session's name because this is the only connection between this talk and the series. Yeah, and next I'm going to talk about large language model, which would be a complete opposite of theories and maybe science, right? Yeah, OK, so seriously, the main topic of this talk is about our recent attempt to guide equality saturation with large language models, and mainly about how we discover and fight against the limitations of the current large language models. OK, so at the very beginning, this work is motivated by the recent huge success of large language models for program optimization. They have been reported to be able to success CUDA kernels, fix practical performance bugs, and optimize complex algorithms for competitive programming. Yeah, and in these tasks, the key advantage of large language models is their rich knowledge obtained from the large-scale pre-training so that they can easily scale up to complex programs and offer large-scale optimizations. Yeah, but on the other side, no matter how impressive these results are, large language models always suffer from the risk of generating incorrect optimizations. Yeah, and recently, as the large language model becomes more and more powerful, this issue has become more and more tricky because large language models have become better to generate plausible but actually incorrect programs. For example, in the work of CUDA optimization, they reported that their agent is so clever that can utilize a memory exploit in their evaluation script, so that sometimes it will hack it, use an incorrect program, and make the tool report a false speedup, which can be as high as 100 speedups. OK, so this is the current stage of large language models, scalable but unsound. And I believe such kind of situation can easily remind us of those traditional techniques, right? Program rewrites, equality saturation, EGRAPHS, because all of these techniques are sound by construction but suffers from limited scalability. So in this work, we aim to answer this question, that is, whether it is possible to combine these two approaches and keep both advantage, and in this way to get a program rewriter or optimizer that is not only scalable but also ensures the correctness. OK, so this is a very natural and straightforward idea, but there's still some huge challenges prevent us from getting such a good combination. So the major challenge comes from the gap between practical rewrite systems and the current stage of large language models. So from one side, current practical rewrite systems have become very complex, so it is very difficult to teach large language model to use such kind of rewrite systems. For example, some practical system can comprise hundreds of customized rewrite rules implemented in thousands of lines of code, and moreover, this code will closely entangled with many external components, such as customized DSL or some external solvers. But in contrast, the current learning ability, especially in-context learning ability of large language models, is still limited. In most cases, they can only capture a very few amount of information in the prompt, which is far from sufficient to grasp the rewrite system. Yeah, and from the other side, from the output side, even if we assume the large language model can understand the whole rewrite system, it is still fundamentally challenging for it to output the correct rewrite chain, because large language model is trained mainly over a pretty high-level descriptions, high-level ideas, but rewrite system usually work on a very, very low level. Let us consider a very simple problem. We call it freshman string. Its goal is to prove that the square of x plus y is equal to the square of x plus the square of y. So clearly, this is wrong, but it is true under a very specialized rule that if we assume every expression plus itself will always be 0. Then for this task is very simple and can be easily described within 100 tokens. But even one of the current best large language models cannot solve it correctly, because in some intermediate step, it will forget to maintain the low-level structures and will incorrectly use the plus operator for different inputs, which is incorrect. Yeah, and such kind of details missing problem will become more and more significant in practice, because usually we will need many different rewrite steps comprising many, many different tokens. So it would be a mission impossible for large language model to keep track of all of these details correctly. Okay, so this is a challenge, and now the problem boils down to how to bridge the gap between large language models and rewrite systems, right? So our solution comes from, it's mainly motivated by this previous work, guided equality saturation. So their key insight is that they find human users are very powerful. They can find useful checkpoints in the rewrite chain, even without knowing all the details. So for example, for the previous task, before going into details, we can easily come up with a roadmap of how to rewrite from the left turn to the right turn, right? So we will know that we should first try to expand the square operator and unfold this multiplication into some low-level sum. And at last, so we need to somehow cancel out this duplicated term x times y. Yeah, so such kind of roadmaps can provide a very strong guidance for equality saturation because we no longer need to rewrite directly from the left to the target expression. Instead, we only need to consider the rewrite from each checkpoint to the next so that we decompose the whole task into much simpler subtasks. Then the scalability can be improved significantly. Okay, so we can easily generalize this idea to our case, right? Because large language model have exposed human-like capabilities in many different tasks. So a natural idea is to use large language model to take the charge of human developers to provide a high-level guidance to equality saturation. In more detail, so given that large language model cannot handle all the low-level details, we can just put it at a high level and provide it only with the task description. And instead, for these low-level things, for example, concrete programs and the detailed rewrite system, we still use the traditional techniques to keep track of it. So in each round, we will first run equality saturation. We run program rewrite with a moderate resource limit. And the only goal of such kind of rewrite is to move through enough low-level details to reach the next checkpoint. It means that we expect this intermediate EGRAPH will contain a meaningful checkpoint for the current rewrite process. And then the remaining problem is how to extract out the checkpoint from this intermediate EGRAPH. So to do this, we will put a query between these two different levels. This query takes the whole EGRAPH and raises high-level queries to the large language model and takes the response and uses this response to pick a checkpoint from the EGRAPH. And once such a checkpoint is decided, the low-level process will move to the next round. We will run rewrite or equality saturation again to move to the next checkpoint and then run the queries again. So this process will repeat and repeat until we find an expected result or this whole process converge. Okay, so this is the high-level workflow of how large language model-guided equality saturation works. And here, the key idea is to use a query to hide all low-level details from the large language model. And of course, clearly, the performance of such kind of framework highly depends on how we design this query. Actually, this design choice is very tricky and suffers from a very tough trade-offs. The first challenge, the first side comes from the large scale of the EGRAPH. Right? We know that EGRAPH can be very large after even a few rounds of equality saturation, and there can be exponential number of programs in the EGRAPH. So it means that we cannot use some very simple queries, like for each program, ask the large language model that whether this program is good, or whether the next program is good, or whether the third program is good, right? Because we do not have enough time to traverse the whole EGRAPH. So this challenge will push us towards the direction to use some more informative queries to get more information in each interaction. But then at this time, we will meet the next side, the next challenge. That is different from human users. Large language model is not very reliable, given that here it takes only high-level descriptions instead of any low-level details. So for example, if we ask it to directly output a checkpoint, then with a high probability, it will give us a very wrong program. For example, it can be syntactically wrong or can even be not equivalent. So to design a good query, we need to find a very delicate trade-off between these two sides. And actually, to be honest, I don't think we have totally solved this problem. So what we have done is to try and evaluate several different design choices. And here I will show you the current best solution we have ever found. OK, so our current design combines a query method and an error correction model. It will run in several steps. So in the first step, the first query is very close to the direct query, but it focuses on subprograms. So this query will first ask the large language model to focus on a subprogram and then provide a checkpoint by modifying only this subprogram. Yeah, but of course, large language model is also allowed to change the whole program. So the main effect of this query is to make it as much focus on subprograms as possible, because it will reduce the scale of new expressions written by the large language model, which means that the total noise introduced will be reduced. Yeah, and even though with a high probability, the result can still be wrong, so we will try to correct these errors during the extraction. So we will use a customized extractor that try to find a program from the graph and minimize the string added distance from the program and the raw output of the large language model. And such kind of extraction can be done efficiently by dynamic programming. And at last, because such kind of extraction may change the program, so we will have a final check with the large language model whether this program is equivalent or better than the checkpoint you suggested. Back to the previous example. So our query will be like this. So first, we will ask for a checkpoint from the initial expression to the target expression. And then large language model will provide us with a wrong expression. And more worse, this expression is too far away from the initial expression, so there is no equivalent form in the current graph. So at this time, the extractor will come up with a very different expression with a very large distance. So with no doubt, it will be rejected by the model in the final check phase. Now how to fix this? So such fail means that the current checkpoint is too far away from the initial expression. What we need is a closer checkpoint. So we will restart a new round of query by asking for a checkpoint from the initial expression to the previous checkpoint. And then at this time, the output will be much more reasonable and much closer to the initial expression, and then the extraction will work well, and this expression will be accepted by the large language model. By repeating this procedure, we can solve the freshman stream problem with a very tough resource limit, where we only allow 3 iterations for each round of saturation. So this is the whole procedure. So after the first round, in the second round, the model will still choose to modify the whole expression, and it wants us to expand the whole multiplication. Yeah, and here during the extraction, we will supply the low-level details to make it correct. And then in the next 2 iterations, the model will focus on the subprograms and try to reorganize these subprograms closer to the target. And after that, the last checkpoint will be close enough to the final target, and then we will move to it in the last round of equality saturation. OK, so this is everything about our current approach. And because this is only an ongoing project, so we only have some preliminary evaluation on it. So what we have done is we try to reproduce the case studies in the work of guided equality saturation, especially the case study on the Lian proof generation. So in the previous work, they built a tool chain that can convert Lian theorems to a rewrite task, where the theorem will become a goal and all available lemmas will become rewrite rules. And they show that with the guidance from the human user, equality saturation can prove some non-trivial theorems. And what we have done is to reproduce all of these case studies by replacing human with large language models and with a very high-level task description provided. So it means that at least in these cases, large language model can provide human-level guidance to the program rewrite. Yeah, and the theorems we have proved covers group theory and the freshman stream task we have seen, and one of its generalized version, and also the proof of the binomial theorem. And among them, I would like to expand a little on the task in group theory, which is pretty interesting. The goal of this task is to prove that the inversion of A times B is equal to the multiplication of the inversion of B and the inversion of A. And the key point of this proof is try to expand the original term by unfolding the identity element into expressions. For example, unfolding 1 to A times A inversed. And by repeating this procedure twice, we will be able to cancel out the original term and get the final term. But we know that generating such kind of rewrite is pretty tricky in equality situation, because it will involve an expansion rule with free variable on the right side. And to support such kind of rules, one pretty complete way is try to use a customized applier to let this free variable to match all possible E-classes. But it suffers from a very significant efficiency issue because it will double the size of the E-graph in each application. Yeah, but what we have found is that such kind of solution is pretty good under the guidance of large language model. So the key observation is that it is not so common to apply such kind of expansion rule in rewrite, which means that once we have to apply it, it will represent some important tricks in the proof, which must be captured by the high-level roadmap or be recognized by the large language model. So with this observation, we can handle such kind of expansion rules in this way. So we can, in each round of rewrite or in each round of equality saturation, we can first run without the expansion rule. And at this time, the proof will start before the trick. And then we can just apply the rules just once, and to let the proof chain move over the trick. And in this way, the trick result will be included in the E-graph and then can be extracted out or be found by the guidance. Okay, so this is everything we have done, and in the future, as you can see, our current work are mainly worked on very simple rewrite systems, which is a little bit different from our motivation. So currently, we are trying to apply our current approach to some more practical rewrite systems, including the Stalinski's rewrite system and the rewrite system for the RISE DSL. The first is for synthesizing structured CD models, and the second is for optimizing tensor-related or array-related programs. And here, there will be many extra challenges. For example, the definition of this rewrite system will be much more complicated, and they will involve customized DSLs, and also this code, their code will entangled with many external components, such as solvers, type systems, and many heuristics. Yes, actually, we don't really believe that our current approach can be generalized to such difficult tasks, but it is interesting to explore how to make it work. At least we have some good news that large language models are actually very good at understanding new DSLs, which we thought could be a challenge before. So for example, in the case of Stalinsky, this is a very complicated DSL program extracted from the left side model. And this DSL is pretty new for the large language model. But what will happen is we only need to throw this whole program to O4 Mini and only hint it that this program describes a CD model. It can perfectly recover what happens in the original model. So its output says that it is a rectangular box with slots, and there's also a shallow backing box on the other side. Yeah, so it means that actually there's some magic in there's indeed some magic in the large language model and can provide some guidance. The only question is how can we extract it out to get the equality saturation. Okay, so this is everything about my presentation, and this is a simple summary. So our motivation is to try to combine these two complementary approaches, large language model and rewrite systems, to make it not only scalable, but also ensure the correctness. And our key approach is to introduce a query to hide all details from the large language model. Yeah, thank you very much. Oh, and at last, I would like to, at last, I would like to thank the authors of Guided Equality Saturation, especially Thomas, because he really provided us much help to this project. Yeah, thank you.
Thanks for the great talk. Do we have questions from the audience? Okay, great.
Hi, thanks for the great talk. You mentioned in the beginning that the LLM has problems because it's trained on high-level ideas and the context length is not sufficient.
Yeah.
I wonder if you could try fine-tuning a small to moderate size language model on something like this, and whether fine-tuning would be like a good strategy to do it.
Yes, that's a very good question. So we do not choose to do so have many different reasons. So the first reason that we do not have enough resource to fine-tune a large language model. And more importantly, for me, I think I want to leave fine-tuning as a last weapon, because fine-tuning will introduce too much different factors and too much reasons to make our work, to make our approach works or not work, right? It depends on how we fine-tune the model and how we prepare the training set and many different other things. So far what we want to do is to check whether large language model can work before introducing fine-tuning. And on the other side, fine-tuning should be complementary to the current approach, right? Because I don't think fine-tuning can solve everything. So what it can do is to improve the accuracy of the performance of the large language model, but with such kind of guidance, it will work better. Yeah, thank you.
Thank you for the great talk. You kind of hinted at it, I think, in the last part with the proof of A, B inverse is equal to, and then the times 1, and being able to split up the times 1. So if I understood correct, the LLM is basically, you're kind of using the LLM to find out when you want to actually turn this rewrite on, because it's like, it just blows up your graph in every other stage, and it's only useful here. So I guess that kind of leads me to my question of like, have you thought about using the LLM to like select which rewrites you want in each stage? Kind of like a more advanced version of this, where you're like, this is the checkpoint here. We need to get to another checkpoint. What rewrites should we continue with? As opposed to just the complete set.
Oh, that's a great question. So yeah, I think large language model can provide many different kinds of guidance, right? So here we just follow guided quality saturation to provide checkpoints. But of course, so its key advantage is that it can understand what should happen during the rewrite. So of course, it can know which kind of rewrite rules should be applied at which stage. But here, I think a key limitation of large language model is that it is too expensive, so we cannot invoke it many times. So for example, if we expect to, in each round of equality saturation, to query the large language model to select which rule to be supplied, then its cost will be too high and we cannot afford it. So there should be a trade-off, but definitely such kind of guidance will work. Yeah, thank you.
I'm going to abuse my power to ask a question that sort of is very related to that, about a sort of alternative form of guidance. For this example that you have here with the group inverse, it turns out that you don't actually need the reverse inverse rule that like expands into 1 over 1 goes to x times x inverse, if you just happened to have A times A inverse just already there in the EGRAPH, right? This was mentioned in an earlier talk, these like magical terms that if they just happened to be there, right, the proof would just go through with, in this case, a more limited set of rewrites. I guess my question is do you think that would be something that would, I guess, generalize to the applications that you're interested in? A form of guidance where it's not necessarily use this rule, but just, hey, give me a guide term that we're just going to put in the EGRAPH. We're not even going to equate it to anything. We're just going to say, we think this might be an important term to think about.
Yes, that's a great question. So I think from a high level, the answer is the same, right? We can expect large language model to provide guidance in any forms. But according to our experience, so large language model cannot do some pretty abstract thing. So what is abstract? For example, writing a sketch is pretty abstract. And another example is that writing a potentially useful term is pretty abstract because it cannot know why this term is useful for equality saturation, right? So, because it cannot understand the very details in EGRAPH or the AG library. So it may not work, I guess, but it is worth trying. So yeah, thank you.
Yeah, thanks for this very interesting talk. So I'm also staying on this slide, and I wanted to ask a question about this magical term as well. So if you go to basically every other lecture, first year lecture on group theory, you will have this proof, right? Yeah. So it's very likely that the data set where you trained the
Yeah.
LLM had this concrete proof and this concrete example.
Yes.
So do you think this will work for things that the LLM hasn't seen before, maybe, or do you think this is so will it generalize for other kinds of things? Have you tested it on other?
Yes,
stuff?
that's a great question. So as a conclusion, so we haven't tested large language model on other tasks it could, it cannot see because it's pretty challenging to construct some data sets that large language model have never seen before. So for the data leak problem, so maybe 1 year ago, my opinion is that large language model can only solve the problem it have seen before. But now I think my opinion is that maybe such kind of tricks is finite in this world. Or for example, maybe 100 tricks can solve 99% of problems. So it would already be great if large language model can memorize all of these tricks and can somehow generalize it to similar scenarios. Yeah, but we will test more on these observations in the future.
Yeah,
Thank you.
cool. Thanks.
Okay, let's thank the speaker one more time.